Good morning or good afternoon, everyone, depending on where you are on Earth, and welcome to this EUROCAE roundtable about standardization of AI in aerospace applications. My name is Christophe Gabreau, and I am a specialist in software processes and certification at Airbus in Toulouse. I am also co-chairing the EUROCAE Working Group 114, who is jointly working with the SAE G34 on the future industrial standard for developing and certifying AI in the aerospace ecosystem. First of all, I would say that there is no doubt that AI has the potential to disrupt the aerospace industry. Indeed, AI will drive solutions that will transform the products and services that are commonly provided by the aerospace company, and with an accelerated pace of change. AI can be based on different technologies of development, and among them, machine learning technologies will revolutionize the current paradigms of aeronautical system development, including those using safety-critical applications. This is the reason why, looking back 2 years ago from now, we are anticipating a growing commercial pressure for artificial intelligence. And so there was an urgent need for regulation to make emerge new norms around the acceptable use of AI. In response to that, 2 working groups were set independently on every side of the Atlantic during the summer 2019. And this presentation is the beginning of a story. So next slide, we are the next slide. So the agenda for this roundtable will be to present ourselves, of course, and we will have a short presentation of the joint group, its objectives and first results. And finally, we will have a discussion between the panelists, moderated by Mark Roboff, who is the chair of the SAE G34. Next slide. So we have gathered around the table several active members of this joint SAE and EUROCAE working group. And now I will let the panelists introduce themselves.
Great. Hi, I'm Darren Kofer. I'm a fellow at Collins Aerospace. I work in our research organization, and I am a member of the G34 committee working on AI and aviation, and also have previously been part of our TCA committee, SC205, which of course developed DO-178C, and specifically I was one of the developers of the formal methods supplement DO-333 as part of that group.
Hello everyone. I'm Corinne Gingin. I work for the Swiss Air Navigation service provider, SkyGuide. I work there for the technical department, where my main activities consist in managing safety and compliance works, projects, activities. I joined the EUROCAE SAE work group for AI at its beginning, and currently I'm leading the group in charge of the data management processes for machine learning.
Hello, everyone. I'm Paula Livio. I'm from Embraer. I work for R&D department. I'm in artificial intelligence research and engineering. We focus on autonomous vehicles on our department as well. And so AI is part of it. And also I'm the vice chair for the G34 Artificial Intelligence and Aviation Committee. It's a pleasure to be here.
And hello, everybody. My name is Mark Roboff. I am the chair of SAE G34. I currently am CEO of Skythread.aero. It's a new venture in aviation, building a consortia-led federated data mart and data exchange for the industry. I have a 15-year background in AI and related technologies. It's a pleasure to be here today.
Okay, thank you. So all the panelists have introduced themselves. So now let's start with the overview, and I'll let you the floor, Mark.
Thank you, Christophe. Next slide, please. So SAE G34/EUROCAE Working Group 114, as Christophe mentioned, is a joint international committee for putting together a means of compliance for the certification of artificial intelligence and machine learning systems in safety critical airborne products and ground-based solutions. So it's building a common standard. It's called a process standard for the certification of both airborne systems and ground systems. So think about, for instance, an autonomous autopilot or an AI managed air traffic control system. We are comprised today of over 500 members. Those are technical fellows, engineers, DERs, research scientists, data scientists, even a few business executives from across the aerospace ecosystem. We have major airframers, of course, Part 25 and Part 23, major engine manufacturers, Tier 1 manufacturers and engineers, of course, the major avionics suppliers as well. We have great support from the UAM or AAM or eVTOL space, however you would like to refer to it today. Great participation from defense companies, both in the United States and in Europe. Research labs, including NASA, and also airlines. We even have a few pilots on the committee. Lastly, it's important to state, and we have fantastic support, global support from the global regulatory community, FAA, EASA, ANAC down in Brazil, Transport Canada, and of course ICAO, as well as regulatory participation from other countries as well. Right now, we are working to deliver by the fall of next year or winter of the year following our first process standard, which it's titled AS6983, which is going to outline a development methodology and certification principles for the certification of AI and machine learning. There may actually be two versions of this standard at the end of the day, one for airborne systems, one for ground, but they're going to be delivered from a common base. In addition to this process standard, we actually already have released a what we call an SAE, an AIR, the EUROCAE equivalent, I think, is an ER. That is a statement of concerns document. So what that does is it imagines an AI development methodology focused on neural networks and examines existing standards like DO-178 and DO-254 and the 330s, and supposes where the challenges are and where the gaps are in being able to certify AI with existing software and complex system development standards. Additionally, we are in the works to produce a taxonomy document that will give the industry a view of how we're looking at the broad scope of AI and AI technologies. And then there will be a following document on use case considerations. So it explores the use cases that we're working on to illustrate the standard that is currently in development. Next slide. So right now, in terms of our immediate concerns, right, we've done a major gap analysis of existing standards. We'll talk very high level about where machine learning development falls down if you were to try to certify it with DO-178 in particular, and it's about traceability and coverage, right? So the fundamental challenge with machine learning is that you're not programming a system to do something. You're giving an algorithm data, right, and telling the algorithm to figure out what we want to do based on finding patterns in the data. That is a high-level description of machine learning. And what is produced from that is a data structure. And we're very much today focused on one particular type of data structure called the neural network. That has qualities about it that can't be logically decomposed the way traditional programming can be logically decomposed, and thus traced to your performance, safety, and functional requirements. So, you know, this is an aspect of the explainability problem in AI. So if anyone in the audience has a background in AI or has read about AI or is a researcher in AI, has probably heard about, if not well familiar with the explainability problem. That is essentially a central issue and question that we're tackling. How can we assess and assure the safety of a component that has machine learning system in it, where we can't depend on the DO-178 and DO-254 architectures of traceability and coverage. There are several industry papers and a lot of industry guidance that we are following and have also in turn contributed to. I want to highlight several important ones to that, including the EASA AI roadmap that was published in January of 2020. For anyone interested in AI in aviation, I think it's a fantastic starting point. It's an easy read. It orients our work, and I think a lot of the work that's happening in the industry around this, and it calls for a timeline in terms of development, where right now, again, we're producing our standard for the fall of 2022, winter of 2023, and that is in support of an EASA goal to have the first machine learning system certified and flying by 2025. That may not be an autonomously flown airliner. That may be an AI algorithm that improves a smaller or less critical function, but it's a starting point. And then we move up from there and mature over the decade to the point where by 2030, we may be having we may have single pilot operation of an airliner, and then by 2035, perhaps zero pilot operation of an airliner. And while the EASA roadmap highlights large transport aircraft in the standard, or in that document, you know, as with us, we're not focused just on one aspect of aviation. We're not just looking at part 25 or part 23. We look at aviation holistically. And again, the executive team on the joint committee is comprised of folks from major airliner, airframers, general and business aviation concerns, and the UAS, UAM, AAM, eVTOL community as well. And next slide. So I talked a little bit about that timeline, right? So again, our first standard is going to be due out in the fall of 2022. The winter of 2023, we'll be following up with later standards as we progress across the decade. As we progress with future standards, all right, we'll be following AI's maturation and acceptance in the industry. So the first standard is going to be looking at how do we adopt an AI ML life cycle into a broader existing systems engineering life cycle, particularly around validation and verification. We're looking exclusively at offline learning. So it's not about AI systems that will learn and adapt as they're in flight, for instance. But as we progress, right, other standards or future standards, I should say, from this Joint International Committee will address other areas of AI and more interesting and I think more critical questions. We imagine a future state, which we'll talk about a little bit later, of how AI and ML may in fact change the nature of certification and vice versa, and what a future model and architecture may look like for how we might certify something like a completely autonomous aircraft. Okay, next slide. Okay, I'll turn it back to Christophe.
Yes, thank you, Mark. So one of the questions we have is how will we integrate the new guidance into the current standards? As you can see on the left-hand side of the figure, the current standards are articulated to propose an end-to-end solution from the system level to the item level. And at some point in time, an intermediate level of abstraction was inserted to handle the model-based development. So if we go to the right and we consider that the data-driven development is the third development paradigm after the model-based, then we can introduce the ML technology by analogy with the model-based standards. However, if the ML model is a new kind of model, the comparison with the EUROCAE standard ED218 or DO331 for the SAE, so any comparison to these standards stops there, because this is not at all the same kind of model as the one used by these standards. And indeed, the differences are big. Well, the ML model is a black box where non-line of code is traceable to a specific requirement. So in this case, completeness, traceability, and detection of unintended behavior will not be possible using the classical means. So new means of compliance should be anticipated. This is the work of the joint working group. We are investigating new objectives in the learning assurance field to guarantee the safety of the systems based on machine learning. In addition, this might impact the system and the item level of engineering, of course, and this is what we are currently investigating in the joint group. Let's go now a little bit into the detail with the following slide. Next slide, please. So, a lot of information in these charts. First, a disclaimer: this process flow is currently ongoing, and it has been extracted from a joint group working document. So, don't consider this flow chart as an approved representation. However, it represents quite well the idea of the future certification approach. In essence, and usually used in the development of embedded complex systems, there are 3 levels of engineering. Level 1, system level, where you can find traditional processes, requirement capture, architecture, and in parallel safety assessment. Level 2, the subsystem level. So as part of the overall system architecture, a subsystem based on machine learning has been identified. Is system guidance also prevail at this level? We know that some activities regarding data will have to be done. Level 3, the item level. This is where the new standard objective will be developed to ensure that ML techniques will properly develop the intended function and will not alter the safety of the system it belongs. So I will not go more details description on this chart. Let's go to the next one. So in order to ensure that all voices are heard and that impact to and from other areas of systems are taken into account, the joint group has established an extensive list of liaisons. Among others, the group interconnects with other working groups within SAE and EUROCAE on topics such as unmanned aircraft systems, UAS, complex aircraft systems, or aeronautical system security. It also works with other standards organizations such as Eurocontrol, AVSI, JARUS, or ASTM, and also with French research projects like the ANITIDIL initiative in Toulouse. And now the long-term vision with Mark. Next slide, please.
Thank you, Christophe. So as mentioned, the big challenge with AI and ML is the black box, it's explainability, right? And when we think about how systems and products are certified across the globe, traceability, decomposition of implementation and connectivity of implementation to requirements, right, is the critical architecture. So we have to think about, well, how in aviation are we going to certify something that we can't decompose, right? And the truth is, we already have an answer because there are things that we certify every day that we don't decompose, and that is, of course, human brains. So we think about how you certify human pilots, how you certify human traffic controllers, how you certify human mechanics, right? And the framework for that, you know, we see as being adaptable to AI and ML. We think about, for instance, you know, the process of certifying a ground school curriculum or a flight school, right? That has parallels to the work that we're doing right now in coming up with ways to define data assurance. How do we know that the data that we collect to train a model is sufficiently representative of the environment and the physics and the subject matter of the model that we're aiming to train, such that we can assure that the model will be trained well? Then we have the concept of the check ride, and this is where I think things get very interesting. So today, take a pilot out on a check ride and judge whether he or she can, over the course of that hour check ride, competently fly an aircraft, right? And there's so many things that one can check for in that hour time. We can imagine constructing virtual check ride happening in a digital environment, right? And taking something like an AI autopilot and putting it into that virtual environment, into that virtual check ride. And if we figure out how to, from a performance standpoint, create robustness requirements for things like simulation, knowing what type of performance functionality a simulator needs to be trusted as a facsimile to real life, if we can create testing and scripting requirements around verification of a model, right, that can make up something like a virtual check ride, then many more interesting things are at a disposal. Instead of an AI system going on a real plane for an hour, you can have an AI system take 1 million virtual check rides at once and in real time and in far less time. You can commute, you can compute and test against orders of magnitude more edge cases than you would be able to in real life. Right. So there's a lot of scalability to this concept, and this concept is not one that we invented. It's been around for a few years. It's called AI licensing, and we see it not necessarily as the single answer, but a critical piece to a multifaceted world in which we can safely certify an AI ML system that, again, has been deemed to be just as safe, or in fact safer, than the systems that we certify today. Other pieces around this, in addition to this concept of AI licensing, may be constraints bounding, where you have defined inputs and outputs to the AI system and are building in safety boundaries across that AI system that limit output. There might be some level of introspection into the setup and the structure of the AI model and the algorithms used to build it. Again, just the same way pilots need medical checkups to stay concurrent with their license. So what we see at a high level is a fusing of two worlds. We see a fusing of how the operational world in aviation is certified with how the engineering world of aviation is certified as being a critical solution or path to solve explainability in AI and ML. Next slide. So just a little bit more about upcoming work that is going to be stood up in the near future around simulation. At least on the SAE side, there is talk now of standing up a new committee that'll be focused on model-based engineering and simulation, to look at how we can take today things that are done in the physical world, things like physical flight tests and other physical training activities, and move them into a virtual world as a next step to advancing this concept of being able to verify in the virtual what today is verified in the physical. When we talk about why, as an industry, we're so interested in this, right? From an artificial intelligence and machine learning standpoint, I'd argue that there are two critical reasons. One is the type of applications that AI and ML bring to the market. We talk about autonomous systems as a flagship, but I'll point out that a big interest in autonomous systems, and not simply that we expect a big increase post-recovery in aviation and are also facing a pilot shortage. It's not about cost savings, at least not to everyone. What I think it is to everybody is it's about safety, right? So for anyone who's listening to this that's a pilot, anyone particularly that may be coming from a military background, you may be familiar with a concept called an OODA loop, right? Which is how folks interpret and react to a dynamically changing environment, right? We observe, we orient, we decide, and we act. Merging the human executive capability, right, in sequencing that OODA loop with the power of computers and with the speed of computation shrinks that OODA loop reaction time dramatically. And when we think about, right, the whole sequence of major incidents and accidents in this industry over the last 20 years, we can imagine how shrinking that OODA loop would have prevented that incident. The other and second reason why, as an industry, we're so interested in this, and it comes back to, again, turning what is done today in the physical world into being able to be done in the virtual world. It's shrinking the delta, particularly the cost delta, in developing the most safety critical application, that DAL-A application, down to what it would cost to develop, say, a DAL-C or DAL-D application. If we can fundamentally change the cost burden of engineering in commercial aerospace, we now enable a huge wave of innovation. And we're seeing that already in the eVTOL AAM space, but right, we still see challenges there. There's still a lot of questions about how costly is it going to really be to develop a fleet of air taxis or a next generation supersonic airliner. We see AI/ML and the shift from the physical to the virtual, right, as lowering that barrier, making new forms of aviation not just possible, right, but practically feasible, taken to production. Next slide. So to close, right, there's a lot of exciting things here, and there's a lot of work we have to do, especially in changing not just standards, right, but cultures, concepts, and entire architectures. Because when it comes down to it, machine learning is not like software programming, right? In software programming, we go line by line. There's a logical connection to the requirements that we're implementing. This is a great little comment courtesy of XKCD, which is a website that has wonderful comics about the life of technology and technologists. And what I love about this is because there's a truth to it, right? AI is taking data, putting it into an algorithm, and seeing what works. There's a lot of trial and error. But there's a lot of trial and error in how the human mind thinks, and there are some interesting parallels to that. So we have to embrace this. We can create structures that assure the safety of our solutions, even with this setup. And we see this transformation as enabling tremendous possibility for the industry. All right, next slide. So I thank everybody for watching our presentation this morning. And right now, I'd like to invite our panelists to the stage where we'll do a short discussion and Q&A in the time we have left. All right. So thank you everybody for coming. I'll kick off on a list of questions for discussion topics we have. So this is a recorded session. So the first one's going to be to Karine. So data is the fuel of machine learning development, right, as we alluded to in that last comment. What are the main challenges from a certification standpoint?
Thank you, Mark. Yeah, we all know that machine learning relies heavily on big volumes of data, and these data need to fulfill some specific characteristics in order to enable the building of robust and sound models, machine learning models. And for instance, the kind of characteristics we expect from these data is that they are representative of the domain where the item will be used. We want the resulting data sets to be independent from one another because they will be used in different manners when it comes to build the model and to verify it. And actually, the main challenge we have in regards to data is that currently the standards do not allow us to provide the assurance that the data are fulfill these expectations we have on them. So because these expectations are quite different from the expectations we have so far in traditional software regarding the quality of data. The expectation we have for machine learning goes beyond that, and the standards are not applicable. This is why we are working on defining new guidelines and new assurance means for data in the context of machine learning.
So my next question is to Christophe. Is explainability mandatory for certification?
Okay, Mark, this is an excellent question, and I think for the time being, nothing is frozen because this is really a new topic, still on the research field as we are speaking. For sure, it's mandatory from the EASA viewpoint because as they define the AI explainability as one of the pillars to respond to a trustworthiness analysis. So it was part of their roadmap they released 1 year ago, and it was responding to the Europe Council request to get transparency in the use of AI development. So, but first, what is AI explainability, we got a definition per the statement of concern. The definition is the extent to which humans can understand, interpret, and account for causality of an AI system or algorithm. That said, what are the challenges? There are multiple. The first one is, well, the ML algorithms are definitely black box entities and that are capable to find correlation in input data to produce prediction. And all is in there. I mean, while a human explanation needs causality, ML techniques only work on correlation. So the problem is, can we find in this correlation the causality we need to produce good quality prediction? This is tricky the question. The second challenge is that even if we think that we can have an explanation, how can we prove it is reliable and correct? Indeed, the accuracy of the explanation is really at stake to demonstrate that it is correctly reflecting the system process to generate the output. But the accuracy is only valuable when the model operates in the limits of its knowledge, exactly as for human. Don't ask a human something it doesn't know, you will have a very low probability to have a good answer. And the third challenge and difficult topic as well is the meaningfulness of explanation. Different actors will need explanation for the prediction, but they won't have the same need and so the same level of explanation. Indeed, a software developer, a pilot, a regulator, or an accident investigator won't need the same level of explanation. So as a conclusion, and in a nutshell, AI explainability will be key, but we are far from having practicable and scalable solution at this point of time.
Thank you, Christophe. Next question is to Paula. Are there some V&V techniques specific to ML development?
Well, Mark, this is a very interesting question. You told at the beginning also, Christophe, that we are based our discussions for these new standards for several industry papers. So, for example, EASA roadmap, Fly AI roadmap, AVSI, and so on. But one thing common that for V&V, when we talk about machine learning, is how when we create and design a machine learning model and we put it in a target hardware, for sure the traditional development of software that is embedded today, we follow many standards like the DO-178 and the supplements like DO-231, DO-323, for example, for formal verifications, formal method verifications. And we see that those they are aligned with what are the challenges for a machine learning perspective. So EASA, they publish on their roadmap a learning assurance process that can be something different from the read process that we have today for a verification process in traditional software, for example. So the W software, the W shape can also be to apply it, in their opinion, and I think it's pretty well, to machine learning development as well. So there are two differences between those kinds of new algorithm, but also the industry and academia, we are searching for new solutions and new techniques for that as well. And I can say that formal verification can be part of it, maybe, and other techniques as well, in my opinion. So I think it's.
Thank you, Paula. All right, I think we may have time for one more question. What are the main challenges of AI and ML software development assurance compared to classical software development assurance? So Darren, you want to tackle this one?
Sure. Well, some of this goes back to the fact that the whole reason that we're applying AI and ML techniques is because we're trying to address a very challenging problem to begin with, one that would be challenging with any technology. So things like vision and perception are good use cases. So that's the first problem. But when we look at the application of our traditional verification and development processes to ML systems, one of the main challenges, and I think you, Mark and Christophe both mentioned this, is completeness, and the fact that we really need some alternative to the structural coverage metrics that we rely upon today. When we when we gather structural coverage metrics for ML systems, typically either it's too easy or trivial to obtain 100% coverage, or it doesn't give us any useful information that traces back to requirements or errors, as Christoph mentioned, no line of code or neuron in a ML system traces back to a particular requirement. So the things that we look for, that we want to discover with in coverage testing, identifying completeness of our requirements, missing requirements, efficiency of testing or verification, and critically discovering unintended functionality. We just don't have those. We don't have a way to get those using the traditional methods that we would apply now. So as far as our standard, our baseline, the things that we're relying on now have to do with trying to establish the completeness and representativeness of the data sets that are being used both for training and for testing verification of the ML components. Formal methods is another way that we might be able to achieve comprehensive coverage of the system behavior, but there we're still in many systems faced with limitations related to scalability or the absence of requirements that can be formalized. So that's still an open question whether that's going to be effective on a broad scale. There's active research in identifying new metrics that can be applied to neural network and machine learning systems in general, and the committee is actively evaluating those. And then finally, looking at runtime architectures and monitors as ways to mitigate these kinds of problems, the ways to use the architecture to bound safe behavior for the system, detect anomalies, and then possibly switch to safe but limited alternative functions if anomalies are detected.
All right, excellent. Well, I think we're just at time. So Darren, Corinne, Christoph, and Paula, thank you very much. It was a pleasure having the discussion, and thank you to RTCA and EUROCAE for having us all here today.